Hello mga ka-Johnny! Welcome back to my YouTube channel. Again, this is Sir Robin Stanipulan, your partner in learning mathematics. Before you proceed in this video, do not forget to click the subscribe button, give me a thumbs up if my video helps you, okay?
Back to my YouTube channel again. This is Sir Robin Sanipulan, your partner in learning mathematics. In this video, we will be talking about the continuation of my previous video. So still rational function. So this video we will be representing rational functions through tables, graphs, and equation. And we believe that these are the things, if you still remember in our function discussion, these are the things, important things that we need to remember in representing function. You can represent this one through tables, you can represent this one through graphs, and you can represent this one through equation, ladies and gentlemen. And what are these three representations that are very necessary once we represent rational function for us to really have this picture, for us to really have the picture on how the rational function works. Okay, so without further ado, let's write deeper regarding the representation of rational function. Okay, so first representation, of course, we will be making the table of values. And I know that you all familiar with table of values. Simply, table of values is we will be composing only what are the numbers that will satisfy the value of x to our given function. So basically, if you still remember, if making I am so sorry, that's very pangit. Okay, so okay, there you go. Okay, so for rational function table of values, we will be creating only tables. Okay, so I have here the x and I have here the y, or my f of x. Okay, in table of values, you simply look for your values of x that will make your equation satisfied. Okay, say for example, I'm gonna put here 1. So this one will be substituted to the given equation. So it will become, what is the value of your x? That is 1. So that is 1 plus 1. And what is your x here? That is 1. So it will become 2 over 1. And 2 divided by 1, that is 2. So meaning the value of your f of x or your y is 2. So you simply put lots of numbers here that will make, again, that will make your rational function satisfied. Example, another negative 3. So you substitute that one to your given equation. So that is our table of values, ladies and gentlemen. So what once that is negative 3, it will become negative 3 plus 1 all over negative 3. It will become negative 3 plus 1, that is negative 2 all over negative 3. So negative divided by negative, that is positive. It will become positive 2 over 3. So therefore, this is now 2 over 3, and so on and so forth. So you simply look for a number that will satisfy for your given equation. So what is the numbers that will not satisfy for the value of x? Obviously, once the value of your x is 0, so basically your denominator will become 0, and that will become undefined. So you avoid the table of values that will make your equation undefined. Okay, so whatever you put on your table of values, simply the values that will satisfy the given function, ladies and gentlemen. Okay, so that is the first representation, the table of values. Okay, the second representation is through graph. Okay, so this important characteristic of our rational function, this thing is what you call the asymptote. Okay, what is an asymptote? Asymptote is the line that a curve approaches but does not intersect. Okay, so asymptote, that is an imaginary line in your rational function where the rational function keep on approaching but never touches. So look at this graph here. So what is the asymptote here? The asymptote is this one, this imaginary line or this red line. As you can observe, I have here a curve. This curve is keep on approaching, so gets closer and closer and closer, but will never touch. Okay, so that is the important imaginary line in our rational function, because once the curve will intersect this imaginary line, your rational function will become undefined. Okay, so it is no longer defined. So this graph will never touch, but it will keep on approaching closer and closer and closer. And that line where the curve will keep on approaches but does not touch, that is what you call asymptote. Okay, that is asymptote. Any line, any imaginary line where your graph will keep on approaching but never touch. But as you can observe here, it will approach closer and closer and closer. It seems like they are touching, but mathematically they aren't touching to each other. Okay, so that imaginary line that guides your graph is what you call the asymptote. Okay, so always remember that one, ladies and gentlemen. So in asymptote, we have lots of things that we need to remember, or we have to familiarize this one. Okay, so let's begin with the vertical asymptote. So these are now the types of asymptote that we need to take note, or we need to familiarize once we are now dealing rational function, because asymptote, ladies and gentlemen, these are very necessary or very important characteristic of our rational function. So this really a backbone or an important thing for rational function, because once you fail to understand asymptote, basically you fail the entire concept of rational function, most especially once we are graphing it and representing this one through graphs. Okay, so this is now asymptote. So let's begin with vertical asymptote. Basically, if I have here when you say vertical, so basically it touches the x-axis. If I have here my x-axis, I my Cartesian plane. So when you say vertical, basically it is the standing a line, right? So basically, a vertical asymptote always touching the x-axis. Okay, so basically, when you are asked about vertical asymptote, so it always touching the x-axis. That is why it is always in the equation x is equal to. Okay, so always remember that one. Okay, so how are we going to identify the vertical asymptote? So in a rational function, you always denote, or that is a vertical line passing through the zeros of our denominator. So meaning, in taking note the vertical asymptote, you have to observe the denominator of your rational function and you have to equate that one. So say for example, I have here f of x is equal to x all over x plus 1. Okay, so how am I going to identify the vertical? First thing first, is this a rational function? So try to consider the three standards that I provided to you. So basically, this is a rational function. Now, how am I going to identify the vertical asymptote of my rational function? By definition here, you observe the denominator. So what is my denominator? What is the denominator of my rational function? The denominator of my rational function is this one. X is equal x plus 1. So you have to write it down here. X plus 1 is equal to 0. So meaning your denominator should be equated to 0. So once you equate that one to 0, you look for the value of x, or use simply transfer this positive 1 to the other side. It will become x is equal to negative 1. So basically, your vertical asymptote now here is x is equal to negative 1. So as you can observe here, vertical asymptote is in the equation form, because as we defined it earlier, asymptote are imaginary line. So these are lines. So once you're asked about line, so you have to give you have describing line is always in the equation form. So that's how you remember it. So again, how we identify vertical asymptote here, you simply observe whatever in the denominator. Since in my problem that is x plus 1, you equate that one to 0. And after that one, you transfer all the constant terms on the other side. So from here, my vertical asymptote, so from positive 1, it becomes negative 1. So therefore, my vertical asymptote is x is equal to negative 1. Okay, another example to have a clear picture how the vertical function works. So example I have here, f(x) is equal to 2x squared plus 1 all over x plus 2 and x minus 3. Okay, so how am I going to identify my vertical asymptote for this example number 2? Same thing. Once you're asked about the vertical asymptote, you observe the denominator. What are my denominator here? This is my denominator. That is x plus 2 and x minus 3. Okay, so since I have two different things, so meaning I have to equate these two differently equal to 0. Okay, so let me show you one. So meaning this one should be equated to x plus 2. Oh, I'm so sorry. Oh my god. Oh, I'm so sorry. Mm-hmm. Okay, so how am I going to identify my vertical asymptote here? I have to equate these two. As you can observe, I have two quantities, so it is already factored out. So I have to equate these two differently equal to 0. So it will become x plus 2 is equal to 0. So it will become x is equal to negative 2. So this is my first vertical asymptote. So second here, I have x minus 3. So that is x minus 3 is equal to 0. So this is x is equal to positive 3. Therefore, so in this example number 2, I have two vertical asymptotes. Okay, so that is negative 2 and positive 3. So it depends to your given problem, okay, or it depends on the degree. So for as long as once you are asked about the vertical asymptote, you observe always, again, you observe always your denominator. No other consideration, only observe your denominator equated to 0 and that's it. So for example number 1, my vertical asymptote is x is equal to negative 1. For example number 2, that is x is equal to negative 2 and x is equal to positive 3 because I have two different quantities here that I need to consider. So that's how you define vertical asymptote. That is a vertical line where your x approaches to, where your graph keep on approaching to but never touches. So basically vertical asymptote, we are avoiding these terms. Okay, we are avoiding this term because once you substitute negative 1 to example number 1, basically your denominator will become 0. So these are zeros of your denominator and we are avoiding this one because in the third criterion that I provided to you, your denominator shouldn't be equal to x. So meaning these are your vertical asymptote where your graph will keep on approaching but never touches, because once it touches to these following terms, automatically your graph or your rational function will become 0 or undefined. Okay, so that's how we identify vertical asymptote. That is the first asymptote that you need to consider. Second here is, after you identify the vertical asymptote, this time you have to identify the horizontal asymptote, ladies and gentlemen. Okay, so basically horizontal asymptote, if vertical asymptote touching the x-axis, so for horizontal asymptote, so from the horizontal, this is now the horizontal lines. Okay, so it is now always touching the y-axis. Okay, so this is your horizontal line. Since it is always touching your y-axis, so basically that is now in the form y is equal to something, or y is equal to any constant that you want. Okay, so if in vertical asymptote we simply observe the denominator and equate that to 0 and solve it a little bit, and there you can get your vertical asymptote. For horizontal asymptote, so we need to consider these three observe these three conditions. Okay, so but before that, it is no longer observing the numerator or denominator alone. For horizontal asymptote, you observe your rational function and you observe the highest degree in both numerator and denominator. Okay, so let's say that n here is the numerator or the highest degree for your numerator, and m here is the highest degree for your denominator. Okay, how am I going to identify my horizontal asymptote considering this following condition? For condition number 1, if n or the highest degree for numerator is less than the highest degree for denominator, or it simply shows that the highest degree of your denominator is greater than the highest degree of your numerator, automatically your horizontal asymptote is y is equal to 0. Let me show you condition letter A for you to have a clear picture on how it works. Okay, condition A. Okay, for condition A, n is less than m, or the n here is the degree of your numerator, the numerator is less than to the degree of your denominator. So let me show you here example. So example, I have your f of x is equal to x plus 1 all over x squared plus x minus 2. Okay, so that is my rational functions. Now observe. So again, for horizontal asymptote, you have to observe the degrees or the highest degrees in numerator and denominator. What is the highest degree for my numerator? Basically, that is 1. So this is the highest degree of my numerator. And for denominator, what is the highest degree? The highest degree is positive 2 or 2. So now, observe, which one has the highest degree, the numerator or denominator? Basically, that is the denominator. If the denominator is greater than the degree of the numerator, automatically, your horizontal asymptote is y is equal to 0. Okay, so again, if your denominator highest degree is greater than the highest degree of the numerator, automatically that is y is equal to 0. If I'm going to change it y cube, since cube is greater than 1, my horizontal asymptote is y is equal to 0. Okay, so if I'm gonna change this one to here, obviously my denominator is still greater than the degree of my numerator, so it is under the condition letter A. So automatically my horizontal asymptote is y is equal to 0. Okay, that's how we consider condition letter A. So that's how, meaning for horizontal asymptote, simply comparing the degrees of your numerator and denominator. Okay, so that is for condition letter A. How about for condition letter B? Let me change the color. Okay, for condition letter B, as it shows here, n is equal to m, meaning the degrees of your n is equal to m, meaning the highest degree, both numerator and denominator are equal. So this is how you do it. Okay, so example here, I have here, let me change the color. Example here, I have f of x is equal to 2 no, it's okay. So I have here, I'm so sorry. So okay, so example here, I have 2x minus 1 all over x plus 2. Okay, so for condition letter B, the degrees now, or the exponent of your numerator and denominator, are equal. As you can observe here, I have here 2x. Okay, what is the degree of my 2x, or the highest degree? That is 1. How about the highest degree in my denominator? The denominator, I have here x, the highest degree is 1. Are the exponent equal? Obviously, they are equal. So if the exponent of your numerator and denominator are equal, what are you going to do is you simply get the number beside it, or the number beside the highest exponent. So since what is the beside our numerator, what is beside x here? That is 2. So you simply copy that one, and you copy also whatever the number beside the highest degree exponent in our denominator. So as you can observe, I have an invisible one here, so you simply copy that one, and therefore 2 divided by 1, that is 2. So automatically, since horizontal, that is always in y, so meaning my horizontal asymptote, that is y is equal to 2. Okay, so that's how you do it. Okay, so again, for condition letter B, if n is equal to m, or the degrees of your n and m, or numerator and denominator, are equal, basically you simply get their numerical coefficient, or the number beside the highest term with the highest exponent. So 2 for numerator and 1 for denominator. So basically 2 divided by 1, that is 2. So my horizontal asymptote, that is y is equal to 2. That is condition letter B. Let me try another example to have a clear picture for condition letter B. So example, I have here f of x is equal to 3x squared minus 1 all over 4x squared plus 2. So obviously, what is the highest degree for denominator? That is 3x squared. How about in our, I'm so sorry, our denominator is 4x squared. Obviously, the degrees are equal. So get the numerical coefficient or the number beside it. So the number beside for our numerator, that is 3. You copy 3. And what is the number beside our the numerical coefficient of the highest degree in our denominator? That is 4. So you copy 4. So 3 divided by 4, that is 3/4. So automatically, what is the horizontal asymptote for this problem? That is y is equal to 3/4, ladies and gentlemen. Okay, so that's how we do it for condition letter B. So for condition letter B, just observe, okay, if they are equal. So get the numerical coefficient and divide it, okay? So for condition letter A is if the highest degree is in the denominator, obviously, automatically that is y is equal to 0. That's how we identify horizontal asymptote for condition letter B. How about for condition letter C? Okay, for condition letter C, if the degree for numerator is greater than the degree of the denominator, automatically no horizontal asymptote. Let me show you this one. Okay, let me erase this one. Wait, need space. Okay, so here. Okay, so for condition letter C, if the degree for numerator is greater than the degree of the denominator, automatically no horizontal asymptote, as in no horizontal asymptote that is provided to you. So example I have here, f of x is equal to 2x squared minus 1 all over 2x plus 2. As you can observe, which one has the highest degree? The numerator, denominator. Obviously, the numerator. We have 2 here, and for denominator, we have 1. As you can observe, the numerator is greater than the denominator. So, obviously, no horizontal asymptote, or NHA. No horizontal asymptote. So, you cannot give. So, that's how we compare it. That's how we compare the degrees, and that's how the conditions that you have to consider while comparing the degrees in getting the horizontal asymptote. Okay, so condition A, denominator is greater, so automatically y is equal to 0. For condition B, if they are equal, you divide the numerical coefficient of the highest degree terms. So that is now the horizontal asymptote if they are equal. For condition letter C, if the numerator or the degree of the numerator is greater than the denominator, automatically no horizontal asymptote. So that's how we identify horizontal asymptote. So we are now done with vertical, where vertical asymptote is observed, through the denominator. And for the horizontal asymptote, it is observed through comparing the degrees, ladies and gentlemen. So that is the first two, horizontal and vertical asymptotes. So now without further ado, let's try to observe the third one. The third asymptote that we need to consider. This is what you call the oblique asymptote. So from the oblique asymptote, that is in the form of y is equal to mx plus b, meaning this is no longer vertical, this is no longer horizontal. So as you can, if I'm going to write it here, oblique asymptote, so the simple term to describe here is oblique asymptote, that is an imaginary line that is slanted already. Okay, so that is slanted already. As I presented to you earlier, there is a possibility that we don't have horizontal asymptote. If you don't have horizontal asymptote, basically you have the oblique asymptote, because in rational function you have to remember that we only have two asymptotes that we need to consider, either vertical and horizontal, or either vertical and oblique. So meaning always that vertical asymptote is always there every time you solve the rational function or finding the asymptote. But horizontal asymptote is not always there. So it depends on the degrees of your polynomials or your rational functions. So if you have a horizontal asymptote, basically you don't have oblique asymptote. But if you don't have horizontal asymptote, basically you have the oblique asymptote. So again, every time we deal rational function, you have two asymptotes that you need to consider. First is vertical and horizontal, or vertical and oblique. Okay, so that's the things that you need to remember every time you deal with rational function. Okay, so from the words of oblique, so simple term, that is slanted. Okay, that is an asymptote that is slanted already. So that is in the form of y is equal to mx plus b. So just a short review, no? Just a short review how y is equal to mx plus b works. Okay, so basically y is equal to mx plus b. That is the standard form for the line. Okay, where m here is the slope, if you still remember, that is in the form of rise over run, and b here, that is the y-intercept. Okay, the y-intercept. Say for example, I have here y is equal to 3x plus 1. So what is the slope? That is 3. And what is my y-intercept? That is 1. Okay, so that's how we do it. If we're going to graph this one here, let me erase this green here. Okay, so once we have a short review regarding this one, okay, so oblique asymptote tells us that it is in the form of y is equal to mx plus b. In your geometry class, that is the standard form of the slope-intercept form of your equation. So where m here is the slope or the rise over run, and your b here is the y-intercept. Okay, that is your y that is your y-intercept. So meaning, once we graph this one, example I have here, y is equal to 3x plus 1. Once we graph that one, we begin with the y-intercept, that is positive 1. So y, so basically this is now located here, positive 1. So for the slope is, I have here 3. So basically, what is the denominator of my 3? That is 3 over 1, because 3 divided by 1, that is 3. So basically, your 3 here is your rise, and my 1 here is the run or the slope itself. So you simply rise 3 and run 1. So that's 1, 2, 3, and run to the right, since that is positive. So this is located here. So basically, if you're gonna connect these two dots, so I have here my slanted asymptote. Okay, so that's how oblique asymptote works. So we are going to get this form. Okay, we are going to get this form in order to describe that oblique asymptote. So what I presented is just a review how this slope-intercept form works in our how this one works in our oblique asymptote. Okay, so now, so how am I going to consider if I will now deal with oblique asymptote, ladies and gentlemen? Okay, so to consider how are you going to sure if you are going to deal with, wait for a while, with oblique asymptote is if the numerator is greater than the denominator itself. Okay, as you can remember earlier, there is a possibility that you have no horizontal asymptote, or that is in the condition letters here, or your numerator, the degree of your numerator is greater than the degree of the denominator. So if that happens, automatically you have an oblique asymptote. Say for example here, I have f of x equal to 2x plus 1 all over x. 2x squared plus 1 all over x. So basically, if you're going to look at it, so you don't have a horizontal asymptote because the degree of the numerator is greater than the degree of the denominator. So obviously, what are you going to do? That one is you don't have horizontal asymptote. If you don't have horizontal asymptote, basically you have the oblique asymptote. Okay. So how are we going to find the oblique asymptote in this problem? In order to find the oblique asymptote, is you simply divide this one. You simply divide this one using the long division. Okay, if you still remember long division, so let's divide this one. So that is now 2x squared plus 1, and that is divided to x. Okay, so you are going to divide that one. In order for you to find the oblique asymptote, you have to divide it one using the long division. Okay, so this is how we do it. So 2x squared, how many 2x squared divided by x, so simply how many x do we need in order to get 2x squared? So simply I need 2, and I need x, so that is 2x times x, that is 2x squared. Okay, always remember that in a division we have to subtract it here. Okay, so that's how we do it. So using the long division, so you have to review the long division. Okay, the long division on how it works. Okay, so 2x times x, basically that is 2x squared. So 2x squared minus 2x squared, that is 0. So I have to bring down 1 plus 1. Okay, as you can observe here, I still have 1 here. Can we divide 1 to x? Obviously we cannot divide it, simply because our remainder here is 1, that is constant, and our divisor is x, so we cannot divide constant to variable. So what is remaining now, since we can no longer divide, so we stop there. Okay, we stop there. As you can observe, I have here the quotient 2x, so automatically this will consider to be your oblique asymptote. So my oblique asymptote now here is y is equal to, what is my quotient? That is 2x. So automatically this is my oblique asymptote. Okay, so again and again, that's how you do it, ladies and gentlemen. Okay, so if you don't have horizontal asymptote, consider that you have oblique asymptote, where the degree of your numerator is greater than the degree of your denominator. And what are you going to do? You use the long division method. Okay, the long division method, ladies and gentlemen. So you keep on dividing until such time that you can no longer divide it. So once you can no longer divide it, you stop. And once you stop, you consider only your constant term here. Okay, no, that's not constant term, the quotient. Okay, so whatever the quotient or the answer of your long division, so that could be your oblique asymptote. So here in my problem, what is my quotient? That is 2x. So that 2x will be considered my oblique asymptote. So that is y is equal to 2x. What is my oblique asymptote? That is y is equal to 2x, ladies and gentlemen. So those are the things. Okay, so those are the oblique asymptote, but those are the asymptote that we need to consider in solving our rational function. Okay, let's try to have some problem here in order for us to really understand the things in representation here. Okay, in representing the rational function. So example number 1, construct a table of values. It's all up to you. So simply construct a table of values here. You create table of values. I have here my x and I have here my f of x. So if my x is 1, so how my f of x becomes? So simply substitute it here. 1 plus 10, that is 11 over 1. So 11 divided by 1, that is 11. How about I'm gonna put negative 2 here? So just substitute it here. Negative 2 plus 10, that is positive 8. Positive 8 divided by negative 2, that is negative 4. What if I'm gonna put 0 here? If I'm gonna put 0 here, obviously your denominator will become 0. So that is cannot be applied. So it will become here undefined. Okay, so that's how we do it, the construction of table of values. Just simply put all the values of x that will make your equation satisfied. Okay, so now let's try this problem. Since I believe construction table of values are okay to you, let's try to solve this rational function. Determine the vertical and the horizontal asymptote. Okay, let's identify the vertical asymptote. Okay, so again, how we identify the vertical asymptote? You observe the denominator. What is my denominator here? That is x minus 1. So what is x minus 1? X minus 1. So you equate that one to 0 and you transfer this constant on the right side. It will become x is equal to positive 1, changing the sign. So meaning automatically, what is the vertical asymptote of this problem? This is now x is equal to 1. This time, let's identify the horizontal asymptote. How we identify the horizontal asymptote? Let me write the equation again. That is f of x equal to 5x minus 1. How are we going to find our horizontal asymptote? Simply observe the degrees or simply compare the degrees of this problem. Okay, so let's try to compare the degrees. So what is the highest degree for our numerator? Obviously, we still have constant here, so we don't have degrees here. So we consider here degree as 0. Okay, so for the numerator is for the numerator, what is the highest degree? That is 1. Okay, that is 1. So that is what is the highest degree? That is 1. So since the numerator is less than denominator, or the denominator is greater than the numerator, so obviously what condition that we need to follow? We need to follow the condition condition letter A. So once the denominator is greater than the degree of our numerator, automatically our horizontal asymptote is y is equal to 0. Okay, that's how we do it. That's how we do it automatically. Okay, so we find the vertical asymptote and we find now the horizontal asymptote. Okay, so that's how we do it, ladies and gentlemen. Okay, so I have here more practices for you to identify. Okay, for number 1 is you simply create or construct a table of values. And for letter B and number 2, you have to identify the vertical and you have to identify the horizontal asymptote. So this problem, I will leave it to you. Just check the description box for the correct answer for these following problems, ladies and gentlemen. Okay, so this is representing rational functions through tables, graphs, and through the following equation of our asymptote. I do hope that you will remember all the terms that I provided to you, all the things that I provided to you, for you to have a really good picture of how to represent our rational functions through asymptotes. Okay, so I do hope that everything is clear to you. This is rational functions through table, graphs, and equation. Okay, so see you in my next video for more videos, for more lessons and understanding of the rational function. Again, this is Sir Robinson Ipulan. Thank you for watching. Bye-bye.